Okay, so we're on to functions now. Now look, we've got this domain here of 0 to infinity, but it says we're looking for the range. Well, we've got to think about what's potentially this going to be. Okay, well, realistically, considering that the smallest that x can be, this x can be is 0, the very smallest that this bracket is going to be is the square root of 1. So the very smallest that this function can reach is 1 itself. Whereas x is allowed to be as large as it wants, so we can technically go up to the square root of infinity plus 1. So realistically, this is going to be infinity. We've got a nice curved bracket on that. We've got 1 mark in the bag. So the first thing I'm going to do with this next question, we've got to find the largest possible value of c, so that the range of g, so that the y values of g are a subset of the domain of f, so they fit essentially within the x values of f. Now f has this restriction on it of it must be positive essentially, so or 0. So having a look at this, we've got g of x, and we can actually, I find the easiest way with one of these is to sketch it out. So this is going to be x plus 3, x plus 1. So I know that this graph is going to look a little bit like this. I know that it's going to have an intercept at -1, it's going to have an intercept at -3. I know it's going to cut here at 3, so we've got -1, -3, and I know that my graph's going to go like this. So bearing that in mind, I can now have a think about, well, what's this greatest value going to be such that this whole thing is positive? Well, considering I'm coming from negative infinity because of my domain over here, to keep this positive, to keep this range of g positive, the furthest I can go without ruining it, without going into this negative zone, well, this negative zone here, the largest that I can actually go is right the way up to the point where I become -3. And I can actually, I can hit that point because I'm still technically within the domain of f, because the domain of f did allow me to hit 0, but really I can't go any further than that. So actually the largest that I can go with this is from this negative infinity back here all the way up to this -3 here. So my domain would look like this. So my c is equal to -3. Well, given that the range of g is the same as the domain of f, that means that what this is going to be able to hit in its values, considering that this range is going to be the same as the domain of f, well, actually this means that the potential things that f can be are exactly the same as its range. It's going to be able to hit its full range. So actually our answer for this, our range of f of g of x, is actually the same as our range of f. So it's not a trick question as such, but it's a question that you've got to think that what g is providing it is exactly what it wants. It's the biggest that it can possibly be. So this is our range. So they've now brought in a new function h to play around with the function f. Now, let's just remind ourselves of the function f from the start of the question. So this is the square root of x plus 1. So we'll need this. So f of x is equal to the square root of x plus 1. And we're looking for f of h of x. So what we're going to get is the square root of x squared plus 3 plus 1. Now, this is actually going to come out as x squared plus 4. Now, it's asked me for the range of it. It's not even asked me for the function. But finding the function helps me find the range. So realistically, there's no kind of restrictions set on h that we need to worry about. And obviously, we know the restrictions on f. But realistically, I just need to look at this and think, well, this is always going to be greater than or equal to 0. So what I'm going to end up with is the smallest that this can possibly be is 0 plus 4, which is the square root of 4. So the smallest that this can possibly be is 2. Then it is going to hit that 2, so we've got that hard bracket there. The largest that this can be is anything it wants, because this x squared could get huge. So we can just go infinity here, soft bracket on it, and we're done.